Okay, so structures. The idea behind structures, when you're dealing with structure, make sure that you use it in 3 stages. You have to define the structure first, then you're going to create and actually point the structure, right? You have to create the map, then you actually make one structure, and then finally you get to use it. So that's the 3 stages that we're going to be working on today, all right? The definition, the creation, and the use, okay? So here's the definition. The definition always have the same shape. It's going to have the words struct followed by the name of the circuit that you want to make. Usually the name that goes in there is all lowercase because this is a data type. Just like float and int and char. You're making your own data type. And the list of variables in the middle is just a list of variables in the same way that the data sheet is showing them to you. So in some sense, the general structure definition is one of those things that you don't have to worry too much about it. It's not like in embedded where we have to come up with it. You don't have to come up with it. The data sheet is going to tell you how to do it. Now, I'm bringing this little piece of code so that you can have an idea where the structure definition goes. This is an example from last semester, all right? We have the pre-processing commands, and right there, together with the pre-processing in a global spot, we just put the words struct, and then you put the user-defined data type. That's this word called space point. You can call it whatever you want. You can call that Bob. Doesn't matter, right? You can call it anything you want. And then you have a list of variables. In this case, I gave you the variables. In the case that we are going to be working together, the data sheet is going to tell you the variables. You don't have to worry about it, right? So how do you come up with this? Is an automated process. For now, I just want to show you the shape of this, all right? So we have struct, your data type, and a list of variables, and then a semicolon at the end, right? Make sure you remember that little semicolon at the end. The compiler will remind you. Okay? So that's how you define it. And then you have to make it. So how do you make it? You're going to use the data structure that you just created called spacepoint. And you're going to type spacepoint followed by the name of the structure you want to make. All right? That's step number 2. And so now point A is going to be a structure, and inside of it, there is 2 variables called x and y. Please remember that this does not occupy space. This is not a variable. If you think about what's happening in memory, the answer is nothing. So this doesn't do anything in memory. This, on the other hand, that makes a structure, and it separates space, and it exists in memory. Okay? So that's the idea behind the structure. So this guy is the structure. So notice that you have to define it first, and then you got to make it. Okay? 2 steps. Define, make. Okay? Now in context, that would look kind of like that. Oops. Like that. So I am using actually the old school struct in front of it, and the reason why I'm doing this is because it is required in the compilers that we're going to be working together. Our compilers for the embedded, the CCS compiler, is pretty much a C compiler, so it's going to force you to put the word struct in front of it. Otherwise, it will not work. But it's just for our compilers, okay? So it goes like this. Definition goes first. After you're done with the definition, you make one. See it? This struct base point, you repeat that. That's the maker. And then this is the actual structure. See that? Does that make sense? That's the only part that I want you to just really keep in mind. I will automize. The process of creating your definition is going to be just automatic. You see, it's just don't worry too much about it. We're going to show you a way to just make it in an automated process. And then the only thing you need to remember is that if you want to make one, you go struct, that name, space, and then you give it a name. And even that name, in our case, is going to be a name that represents a circuit. So even that is going to be pre-chosen for you. So 90% of the time, this is going to be an automated process. Okay? Any questions on this? Okay, I don't want to spend too much time on this particular point, but I wanted to make sure that if you write a name between the semicolon and the closing key, or the curly brace, in your definition, this point A right there is a global structure. Okay? It becomes a global structure. So that means that this point A is a structure that has inside X and Y and is already in space. It is in memory. So inside of main, you can start using point A. It is something that I do not recommend in general terms. If you're using this for information purposes, I usually don't recommend it. But there are some special circumstances that will allow us to do something like that. For now, the only thing I want you to remember is if you put a variable between the curly brackets and the semicolon, that becomes a structure. Right? That's all you need to remember out of this. And even that is not a big point. We can actually bypass this, and it's not going to make that much of an impact. Okay? So that's the idea. Now, the access, so this is definition, this is the creation, and that's the use, right? Definition, creation, use. It always goes into that sequence. So we got definition in the main area. Before the main program goes definition. Inside of the main, I can make one, and then I'll use it. All right? And so the important part to remember is, and this also is not that important because what I'm about to make next. So I want you to keep your eyes in the prize. This sounds interesting, but I am not very interested in this. I just want to step you logically to the spot I want to go to. Okay? This is nothing more than we're just going to wave our hands a little bit so that you can remember how structures were done. And then we're going to step you into the actual place I want you to be. Okay? So here's my structure, and that's how I access internal elements of the structures. Right? We use dots. All right, good. Now, pointers to structures. Here's where I really want you to be. And the reason why I want you to combine these two is because the pointer gives me access to the hardware, and the structure let me split the data inside in logical units. Okay? That's the idea. That's the concept. So we're going to declare the structure or define the structure, right? And this is the spot that goes before the main. Then you need a pointer to the desired structure type. Then you connect the pointer, and then you use the pointer. So in the previous example, I make the definition of the structure. I make the structure. I use the structure. In this case, I create the definition of the structure. I make the structure. I make a pointer. And then I use the pointer. Right? I need one more step. So how does it look like? It looks like this. Okay? We go. So you declare it. Define it. Declare it. I need to just pick one, right? So you have your declaration. So we go like this. We go struct, data type, and there is the stuff that I want to make. Okay? Down here, you can make a pointer. I made a pointer of the same data type. Notice that this data type has to match that, right? That's why I color coded it. See that? See the connection between these two? Okay, good. Any questions on that? You see how it goes, right? Now, it goes like this. Once you have the pointer, I'm going to create a structure of the same mystruct type. Notice that this mystruct is the same as this mystruct, and this is the name of the structure. I have now a structure that inside of it has these two guys, and this is just a pointer that right now is pointing nowhere. Okay? You see that? Okay. Here we go. If I made a connection, I haven't shown you the connection yet, but if I made the connection between these two, in order for me to access the elements of pointer, you use the structure arrow the value of x, and you make it equal to whatever value you want. What this is going to do is that it's going to deposit a 10 in the value of x inside of my first structure. Does that make sense a little bit? There is a missing instruction in here that I need to add, so let me add it right away so that it doesn't create a lot of confusion when you get this. But you need to connect it. And the connection happens like this. You go pointer equals the address of my first structure. All right? Like that. Oh, that's a horrible color. Better. That's the actual physical connection. I take the pointer and I point it to the structure. All right? This still is just a, please remember what happened in embedded. I'm going to make it even easier. Right? I am just like those commercials. It's not for $100. It is not $50. It is not $20. It is actually 29 payments of $5.99. Right? So the idea is that I want to make this even simpler. This, what you saw in here, what you just saw so far, is the actual progression that we took in the embedded class. And the idea behind it is to arrive to this conclusion. Here we go. This is just an example on how the thing looks. I'm not very interested in this. I'm going to leave it out there for you to see. I'm going to post this online and you take a look at it. Here is where I want. I want to use the structure as a tool. And here is where I want you to pay attention. I'm going to simplify the process. I'm going to make it very simple for you to understand the reason why I'm using this tool. Here it goes. Every time you create a variable, be it a pointer or a normal variable, okay? In a microprocessor that is 8 bits wide, you can make the assumption that that specific variable is subdivided in 8 individual binary digits. Right? In general sense, when we talk about a register, we're talking about 8 individual circuits. Correct? I told you that the idea of the structure is to create small logical groups within that variable. Okay? I'm going to subdivide that group. I'm going to create teams from within the variable. So it goes like that. If I do struct my variable division, and this is just a data type, I could have called that cat. Doesn't matter, it's just a name. That's just a data type. Inside, you're going to break this register into components that together, they're going to give me 8 bits. See that? So, for example, in this case, the first variable that shows up inside of this definition or declaration, the first variable is always going to be attached or associated with the least significant bit inside of that variable. So, if you have low bits, 4 bits associated with that variable, that means that we start from the least and we go 1, 2, 3, 4. These 4 guys together are connected now or will belong to low bits. I just created a connection of 4 bits into that variable. See that? The next variable is going to take right after this guy ends. So this guy ended on 3. This guy is going to begin at 4, and then I'm going to have 4 more. So it goes 1, 2, 3, 4 for a total of 8. See that? You can create any combination you want, right? You can make 1 and 7. You can go 1, 3, and 4. You can go 2, 2, and 4, or whatever you want. It really doesn't matter. The only thing you need to remember is the following. If you're going to use this tool, all the groups that you make have to be neighboring. You cannot create groups that are not neighbors. Not with this tool. Right? So I cannot make a group that contains 0 and 2 but not 1. You cannot do that. They all have to be neighboring circuits. Okay? So low bits works because I have 4 neighboring bits. And high bits work because I have 4 neighboring bits. Okay? No way to change the sequence when it comes to the actual hardware. Remember, that's a circuit, and that has a physical location, which means that in software, you cannot bypass the physical location. if I make this name cat, then cat takes this 4. The first guy who shows up in here will take the first few least significant bits. Make sense? Okay, good. Now, here it is. I told you that I'm going to make this really, really easy. Way easier than figuring out how to say small when you order your coffee at Starbucks. So here's how it goes. You have a circuit. The data sheet gave it to you. The name of the circuit is already known. The name is T3CON. That's the name. So, when I begin putting a structure to my circuit, the first instruction is going to be struct followed by T3CON. I tend to use a lowercase. Why? Because I'm a Java guy. I've been doing Java for a long time, and there is a very specific way that I build my variables. It's a bad habit. So I brought that habit back into C language. But that's me. You don't have to put the underscore. I do. I have a very specific reason why I do it. So, at the end of the day, the only thing I want you to do is this. Do not call the data type capitals. It's not a good idea. The underscore, you may or may not put it. You don't want to do it, you don't have to do it. I like to do it because it just keeps my mind in the right place. So I go struct underscore the name of the register all in lowercase, right? All right. I open the key, and here's what I'm going to do. I'm going to take a look at all this circuit. I'm going to show you how to determine when these circuits work together and when these circuits work apart. Okay? So that's the first determination you have to make. Because this is deterministic. There is no variability to this. The circuit will tell you exactly how it's built. For example, look. The least significant bit is called TMR3ON, and there is only one circuit. So I go int, name of the circuit, colon 1, because it's 1 bit. See that? Next circuit is called TMR3CS. So I go int, TMR3CS, colon 1, because there is only 1 bit. And I continue. T1 sync. There is T3CCP1. There is these guys. Now, I know ahead of time what's happening here because I cheated. I look at the data sheet. It's not because I'm smart. It's because the guys already told me what's in here, right? So it's not that I'm an amazing magician. They told me. So I know that this guy, the T3CKPS0 and the T3CKPS1, together, they do one job. Together. So here's what I'm going to do. I'm going to make one variable for both. Okay? And I'm going to put a lowercase x to denote that these are different or multiple circuits. So I go like this. I go T3CKPS little x. And then I go colon and the number of circuits. There's 2 of them. So I know that this circuit contains 2 bits. See that? You okay with that? All right, and then finally, I got my T3CCP2, 1 bit, and the circuit called RD16, that's 1 bit. And if I count this up, I got 1, 2, 3, 4, 5, 6, 7, 8 bits. So I know that my structure is right. The pitfall is that we like to start reading from left to right. So usually, quiz 1 and exam 1, most of the mistakes you make is that you want to start from the left. But don't start from the left. You got to start from the least. So the first line is the least circuit. So you go from right to left. Does that make sense? You see that? Okay. So that's the idea behind naming conventions. So here's the deal. I'm going to give you a little bit of info. That's an individual circuit. That's an individual circuit. And so is everybody else in this register. There are no teamed circuits. Can you write the function declaration for that circuit? All right, go for it. Give it a shot. Just starting your I'll get you started. I'll tell you how I start. You can start it any way you want. I'll tell you how I do it. I'm going to start with this. I'm going to go struct underscore. The circuit name is PIE1. So I'm going to go lowercase PIE1. And then I'll let you finish the rest. Go in the middle. Start building it. Always remember, start from the least. Right here. And they're all individuals. Every single one of these guys is an individual circuit. It's P-I-E, yeah, pi, like pi, P-I-E.
I mean, so
Or TMR.
Oh, TMR, I-E, I-E, it means interrupt enable. It's a master switch, it's an on switch. Yeah, they're all IE, IF, or IP. We'll go into that next week. We'll explain what the enable, flag, and priority really means. And this particular exercise is going to show up in like 2 problems in the test, and it usually is about 20 to 25 points in the first test is going to be on this. Just creating your own structures to attach circuits to it. So make sure that you get this skill down because you'll see tons of it, okay?
So 2 of them work together?
No, they're all individuals, every single one of them. So I'm going to get you started here. I'm going to go with int, and then capital is TMRI or TMR1, IE, and this is one circuit. See that? It's kind of like standard. It's like really standardized stuff. So the next one is called TMR2IE. So I'm going to go int. I'll show you how you determine if they're together or not. It's very easy. The data sheet tells me also. So it's not. So you go int TMR2IE 1 bit, and then you go. The next one is CCP1IE. So int CCP1IE 1 bit, and then you keep going one at a time until you hit PSPIE. Make sense? A little bit? So all these ideas of structures and how do they work and how do they connect, at the end of the day, their expression in embedded systems is mostly found in the distribution of circuits according to the data sheet explanation. That's it. That's what all boils down to. All that suffering about points in space is to get you to this point so that you can understand that I can separate variables inside of a structure and then isolate them so that I can deal with them on a one-to-one basis, right? All these conversations about data not going from one structure element to the next simply says that when I'm dealing with this value, I will not bleed data into any other circuit so the behavior of the circuit is protected. That's it. That's it. This is how we go from here's how an engine works with here, have the keys, let's learn how to drive, right? And you notice that driving is way more fun than just, unless you're a geek, in which case you really enjoy fixing engines, but that's another story, okay? All right, so what about this one? I'm going to give you a little bit of information about this guy. Here's the information. The first 4 guys create one logical circuit, and these two guys are individuals. And these two guys are not connected to anything. So this is unconnected. Whatever you do to that bit is not going to do anything to the circuit because there is nothing in it. Okay, so you have a group of 4, 2 individuals, and an unused group of 2. Can you create a structure for that? Right? So give me the structure for this guy. I'll get you started in my style. You can create your own style, but I like to go AD Con 1. Who wants to give me the first line? We got to start with int, right? So we go int. We go PCFG. What do you want to do? Little x, right? So we go PCFG little x colon and then 4, right? And that gets those 4 together. And then we do int BCFG0, and then that's 1 bit. And then we do BCFG1, and that's 1 bit. And then we go int, and then I'm going to put unused, and I'm going to say 2 bits. And that gives me the proper register, right? Okay?
So, if a bit is attached to another bit, is it always attached to the bit on the left?
Yes. They always make sure that all the bits are together. There are some exceptions to this rule, and those are the head scratchers. And you try to figure out what was this guy thinking when he built this circuit. Because sometimes they separate bits in 2 different registers, making it really hard to put data together. Not really hard, but harder, right? It's like, why do we have remote controls for things? It's because we don't want to walk to the TV, right? Same thing. It's like, it's not really hard. It's just like annoying because you're used to this. All members of the same team together in the same spot. That allows me to now exploit my software to the best of its ability. We got this? Make sense? You see how it's all kind of like predetermined. It's the same outcome every time. There's nothing really special about it. You just go struct this guy in lowercase, key, and then you go these 4 guys, and then that guy, and then this guy, and then these 2, and then close the key, semicolon, I'm done. Yes?
Why would it get the BCF together?
I'll explain that next week. The data sheet tells me, actually. It turns out that even though they're named the same, they have 2 distinct uses. They're not together. They don't work together. We'll explain that next week. That's a very good question. Very, very good. All right. So here's one. Let's use it. Okay, so given the proper structure definition, once I have the definition done, they gave me this. How do I go about using it? And this is the part that excels, right? Notice that the reason why we shifted into structures is because I told you that in the instruction to set a circuit, the name of the circuit is not there. So I don't see it, right? And here's the beauty about this. If I'm going to set that circuit, and I know there is only 1 bit, set means to make 1. So now your whole instruction boils down to this. It will be AD con 1, all in capitals. I'll explain this in a little bit. And then you go arrow to VCFG1, and I'm going to make that guy a set. So this is a set operation. There's something missing in here, and I'm going to show you what is the missing link in just a little bit. But I want to make sure that you understand how the functionality of what we're trying to do becomes easier for my mind. Because down the road, I will take a look at this, and I know that there is a register called ADCON, and inside of it, there's a circuit called VCFG1, and I am making it a logical 1. That is way easier than having to bit mask it. The bit masking is not hard, but down the road, you really, really have to remember. See that? So let's say that I want to reset BCFG0, right? How do you reset? So you go, well, AD con 1 has a circuit inside called VCFG0, and I want to reset it. There is your reset. See that? So in some sense, if you really think about it, the reason why we're going to start using structures is because they make logical sense. It allows me to read my circuits in an easier way, right? And so here's the idea. Here's the whole idea. If I can make you use simple software tools so that you can forget the software for 1 minute and concentrate in the behavior of the circuit, you will be a great programmer. See, it sounds counterintuitive, but the best programmers are the ones that make the least amount of code, at least in the firmware world. Why? Because you're exploiting the features created by the architect of the hardware. That's the trick. And it took me a long time to figure this out. It's just like in music. The idea is not to show how great you are, it's to make it sound good. Right? That's the idea. And so the same thing in programming. Make sure that as the semester is moving along, we're actually taking into account what was the circuit intended to do. And so we're going to try to exploit that behavior to see what is the behavior of every single one of these circuits. Make sense?
So how do you toggle?
That's a very good question. The thing about toggling, because of the compiler that we're using, we cannot use a shorthand. Our compiler has an issue with it, but if you want to toggle it, you will go AD con 1, this guy, and then you go AD con 1, this guy, and then you toggle it. This is a toggle. The compiler that I tend to use, I have an AIR compiler for my day-to-day activities, and that compiler allows me to use a shorthand on pointer to structures, but the compiler CCS don't let us do it. But that's a toggle. Okay? And then if you want to do the read, then it will be like this. So this will be the input value. So I'm going to call this data. And then you simply do AD con 1 VCFG0. That's a read. I reveal the value and save it in data. So that's your read. This is your set, reset, toggle, read. But notice that everything you do contains the name of the register and the name of the circuit in question. You notice that? And that's why I go after structures. Because 5 years down the road, I open the circuit and I look and it says AD con arrow VCGF1 equals 1. And says, okay, I'm setting that bit for reason whatever. Yes?
Why does it change from G1 to G0?
There is no reason. Just let's say that I want...
Isn't that a different bit though?
This is a different circuit. That is this circuit. I just said, what if I want to reset that guy? Yeah. That's a good question. I think let's just rewind this and make it easier, right? So that there is no confusion. So I'm going to do this and this and this, and then I'm just going to go with this and this and this and that. And then now there's no confusion. The examples are great in my head all the time. They make sense in my head 99.99% of the time. But it's making a little bit of sense, right? I think that the whole idea is this. That's easier. By far. It's a simpler way of doing work. That's all there is to it. Okay? So that's it. We're done. That's it. That's the review. So I'm going to post this online so you gain access to all the stuff that we did today. I'm going to try to get this online before I come to class so you can have it and make notes if you want to make notes, and you can follow me at the same time. The reason why I did not broadcast it is because we were looking at the college has a technology called something GX, which is it's a place in where I can actually put all my slides and run the slides, and you can actually open a link in your computers, and while I'm moving through the slides, you can see the link moving with you. So you could be in your home, just sitting there, listening to the class, and watching the slides go by. You can't see the board, but at least you can see the slides moving forward. So we tried to use it, and we failed miserably. So we were just attempting. So it's going to take me a little while to get all the technology right, but hopefully the idea is that I want to make sure that you guys are not penalized for having a job, or you couldn't show up for some reason, and I want to make sure that you have all your classes available. Anyway, I'm just going to cut it here.